Up next, we have Tim Beiko from the Ethereum Foundation. He is the facilitator of the Ethereum All-Core Devs meetings. And for those that don't know, that's where protocol changes are like proposed, facilitated, and like implemented. So super awesome work. I'm super excited to hear from him. He was formerly the senior protocol manager at Consensus, working on their mainnet protocol team. And if I'm not mistaken, he was a big proponent and advocate for EIP 1559. So I'm super stoked to have him here. I hope you guys are too. And I'd like to invite Tim onto the stage.
Oh, there we go. Tim.
Welcome, Tim. I have both Tims. Hey, Tim, you there?
Okay. Hey, can you hear me?
Yep. You're good to go. The floor is all yours.
Cool. Hopefully you all can see these screens. My name is Tim Beiko. I work at the Ethereum Foundation. Over there, I run what's called the All-Core Devs calls, where the different client developers and researchers on Ethereum kind of get together and discuss upgrades to the protocol. I'm just going to walk you all through the Ethereum roadmap, basically what we've done over the past year and what you should expect going forward. So looking back, we had several upgrades in 2021. The first of which was called Berlin. So every one of these upgrades typically introduces a bunch of changes, and at the time there's kind of a major one that is kind of anchored around. And for Berlin, that major one was a fix to a potential denial of service vector on Ethereum, where some operations on the network were underpriced in terms of gas relative to how long they actually take to execute on a computer. And so an attacker could have created a block that would have taken more than seconds to execute. And because of that, given that blocks come every 13 seconds or so on Ethereum, you could have basically stalled the chain if you ran with this attack. So what we did in Berlin was we basically raised the gas costs of those operations, which take longer to execute than we had previously thought, and kind of mitigated that denial of service. Alongside that, we also introduced the concept of transaction envelopes, which would be useful later on to add more different transaction types to Ethereum, and we'll talk about that quickly. And then we also repriced some pre-compile, so just a small gas adjustment. In the summer, in August, we had the London upgrade go live. The biggest change there was EIP 1559, which was a massive overhaul to the market, which in and of itself could be kind of a full talk. And that actually leveraged the new transaction types that we introduced in Berlin. So having that groundwork there was really critical. Alongside 1569, we also added a couple more things. The first is we reduced the amount of gas refunds for a bunch of operations. And the reason there was that refunds were meant as a way to incentivize application developers to kind of clear the storage that they make on Ethereum. So say, somebody has an ERC20 balance and it goes to 0, to just completely delete that address from the list, you would get a small refund. But over time, people have kind of abused that mechanism and created what's called gas tokens, where they would fill up kind of the network with junk data when transactions were cheap, and then clear that to get refunds when transactions were expensive again. And the problem with that, aside from kind of the instability it creates and filling the network with junk, is that the refund you get for gas is not counted towards the block gas limit. So if the block gas limit is 15 million or 30 million gas, then these refunds would kind of be spent on top of that. And that meant that we could get blocks that were effectively 50% bigger than what the actual gas limit was. And because EIP 1559 kind of doubled the maximum gas limit when it was introduced, we wanted to reduce the amount by which this kind of shadow gas limit could be grown using gas refunds. And then finally, we did two more changes in London. The first is we set the foundation for future EVM upgrades. The big challenge we always have when we want to upgrade the EVM is not breaking existing contracts. So what we did in London is we looked at contracts on mainnet and tried to find a byte which no contract started with. So that byte was 0xEF, and made it illegal after London to deploy a contract starting with that byte. And what that means is that now we can use this byte to basically identify future contract versions, which the EVM could interpret differently. And that's really good because it means it kind of allows us to make changes to the EVM, but then have kind of all of the previously running contracts run with their current rules. And then lastly, we also delayed the difficulty bomb, which is a mechanism in Ethereum that kind of slowly makes mining harder on the network. And we'll get into that a bit more after. That was it for London. The last upgrade we just had on Ethereum was the Altair upgrade. And differently from the first two, this one actually happened on the Beacon chain, not on the proof of stake network. And it was the first time we upgraded the Beacon chain since it had launched. So the Beacon chain literally launched a year ago today. It hadn't been upgraded before. And so Altair was the first time we kind of got to test this mechanism. And then the two main changes that were introduced were raising the inactivity and slashing penalties to their expected amounts. So when the Beacon chain went live, the penalties were lowered a bit just because it was quite new and experimental. And now that it had been live for about 10 months, it felt like the right time to just raise the penalties up to their kind of regular amounts. And then finally, there was a change to how validator rewards are calculated. So that's what we did so far in 2021. We have one more upgrade coming, which is called Aero Glacier. This is just a small network upgrade which pushes back the difficulty bomb, ideally for the last time. So we're hoping that the next time basically doesn't happen, and we've just moved to proof of stake already. So this upgrade is scheduled for next week, block 13,773,000. Should happen midweek, so around December 8th. If you run an Ethereum node, now's the time to upgrade it. The versions on the screen right here are the minimum versions that you need to run to support this network upgrade. So that's what we did in the past. And going forward, there's really one main thing we're focused on, which is the merge. So Ethereum's transition from proof of work to proof of stake. And it's worth taking to explain how we actually got to our current basically design and architecture for the merge, going all the way back to kind of the original Ethereum 2.0 world, which I think a lot of people are familiar with. So a few years ago, we had this idea of a roadmap that was in 3 phases, phase 0, 1, and 2, where you would first deploy proof of stake, then you would deploy shards that would kind of hook on to the proof of stake chain, and after those shards had been deployed, you would turn on computation in them, and that's what was called execution environments. So we started working on that, obviously got through phase 0, deployed proof of stake, but in parallel, we saw rollups becoming a very kind of popular way for applications to scale, and also something that was getting to production much faster than sharding and execution environments were. So about a year ago, I think, there was this idea of, well, maybe we should focus on actually going all in on rollups to scale Ethereum, rather than going first through sharding and then through execution environments. And what we could do is kind of keep the same architecture where we'd have the proof of stake chain. Instead of having many shards, we would just have a single shard, which runs the EVM. And then we would have the rollup chains, which actually scale the computation. And then in the future, if we wanted to make rollups cheaper, we could just have extra shards, which would store only data and not computation. But that kind of went from a must-have that was blocking the scaling of computation to a nice-to-have, which could just scale rollups even more. And so there was kind of this push to move towards, using rollups as the main scaling solution for Ethereum. And then kind of the final iteration that came out to that was, well, what if instead of using kind of a single shard to run the EVM, we just kept running it as it runs today and coupled the Beacon chain Ethereum clients that we have. So the clients like Geth, Nethermind, Aragon, and Besu are already built in a way that they support multiple consensus mechanisms. So for example, even though mainnet runs on proof of works, all of the test nets and private network run on different consensus algorithms. So the idea there was saying, what if we just had these clients switch their consensus algorithm to listening to the beacon chain. And this way, we don't even need a single shard for the EVM. We can just keep the current chain running and then have its consensus come from the beacon chain. And this is what we call kind of the executable beacon chain. And this is what we're going for today. So to dive into this a bit more, this is merge node architecture will look like at a very high level. So an Ethereum client will be the combination of both a beacon node or a consensus layer client. Today is kind of referred to as an ETH2 client, and then an or kind of an execution layer client, which today is basically an ETH1 client. And so this beacon node is in charge of the consensus for the network. So it is the component which tracks the head of the network, gets the new blocks, shares the blocks that it gets, and receives validator rewards for doing so. Similarly, the execution engine is what processes and runs the actual transactions. So this is where kind of the EVM execution happens. This is where the mempool is maintained. And this is where things like state management and sync are also done, which is most of the functionality that exists today. The only real difference is that you're moving the block networking up to the beacon layer rather than the execution layer, which we have today. But aside from that, all of the functionality of the execution layer is basically preserved. And as you can see on the graphic, both layers would keep their set of APIs. So if you're using JSC on the execution layer, nothing there would break. And if you're using kind of your beacon APIs on the beacon nodes, nothing there would break as well. And then they both also maintain their set of peers so that, blocks gossiped on the beacon layer would kind of get gossiped to whatever peers that node has. And then transactions gossiped on the execution layer would go directly to the execution engine. And then the only thing we need to introduce is kind of a communication layer between those two things, which we call the engine API. So the engine API is just an API where the beacon layer is able to query the execution engine for various things, such as verifying the execution of a block, requesting a new block, and so on. And to keep things simple, all the calls directional from the beacon layer to the execution engine, and the execution engine just responds to them. Into this a bit deeper, what we get is kind of the following. So we're going to move what's basically in a current ETH1 block into the beacon chain blocks. And people who are kind of familiar with this might know that today the beacon chain produces blocks which have a lot of metadata about the consensus layer. So you can see this on the picture, like the parent root, the state root, the graffiti, randall, all the attestations, new deposits, the exits. But there's not actually anything being executed in those blocks. Whereas on the execution layer today, we also have some metadata around proof of work, but then we get everything that, say, users generally think of as being in a block. So things like all the list of the entire transactions, the base fee, and so on. And so post-merge really things are merged, where you keep kind of the metadata of the consensus of the beacon chain, but then you also include what is now called an execution payload, which is kind of the contents of what a current ETH1 block contains. And it's worth noting that there's a couple small changes that happen at the block level. So the first is that block times go from about 13 seconds with a lot of variance into it under proof of work to exactly 12 seconds in proof of stake, except in cases when slots are skipped because a validator might be offline, which is about less than 1% right now. There's a bunch of fields that'll be set to 0 in the blocks because they no longer apply. So anything that's related to proof of work or Omer or Uncle blocks, because those things don't apply in proof of stake, they're all set to 0. We're not removing them right now from the blocks just to not break any tooling, but you can imagine in the future this might be fully removed. The thing that actually changes in value, though, is the difficulty opcode. So this opcode used to map to the difficulty value of a block. And because this is always going to be 0 now, and that the main kind of use case for this opcode is providing pseudo randomness, we want to have it point to 0 after the merge because that would break a lot of use cases. So instead, we're renaming the opcode to random, and it's going to return the value from the randall in the beacon chain. so that applications can basically use this as a source of pseudo randomness as well going forward, and nothing should break at the smart contract layer. And one kind of quirk to note that's interesting is that the random value is much bigger than the difficulty value. So if your application wants to query whether it's past the merge or not, this is kind of a neat way you can do it, where you can just look at kind of the size of this value, and if it's bigger than whatever the cap for difficulty was, then you know your error. So how the merge actually works. Basically, we need to go from proof of work to proof of stake, and we cannot take Ethereum offline. So we need like a fully online transition process where we can go from being on proof of work to being fully to proof of stake. So there's a couple steps here. The first is that we decide a total difficulty value. This terminal total difficulty value is basically the difficulty that we want to see on proof of work before we start the transition. And the reason to use this, except a block number, is it's just much more resistant to attacks on the network, where a miner could potentially mine a bunch of blocks with, say, a very low difficulty in the future. And if we had like a block number, during the process, they could reveal that change and whatnot. A terminal total difficulty is much harder to fake. So, before that TTD value is hit, the clients will just kind of wait around and keep doing what they're doing. So on the proof of work side, we'll keep producing blocks. On the proof of stake side, it'll just check every block and say, hey, has the TTD been hit? No, just keep moving. Once we see a block whose total difficulty is bigger or equal than this terminal total difficulty, we deem it the last proof of work block. And then duties for block creation move to the validators on the beacon chain. So whichever validator is kind of slotted for the block after a block which exceeds the terminal total difficulty will then produce the first block on the beacon chain. And one thing that's important to note here that people might realize is this kind of implies we can have multiple final blocks, right? So because we're just using a terminal total difficulty value, there might be competing miners that all produce a final proof of work block. The one thing to note is those blocks will not be able to have kind of ancestors. So the only block, kind of the last valid proof of work block, is the first one which exceeds the TTD, and then their ancestors would not be valid blocks. So this means that in the worst case, we're just selecting against like a bunch of competing chain heads, but we're not going down like multiple levels in the fork. And then it kind of becomes up to the beacon chain to resolve that forking mechanism. So the validator will choose which block to build on, and then the next validator will build on that block, and so on. And then what we want to see is the first post-terminal total difficulty block on the beacon chain being finalized. At that point, we have a block which we know is final, and we can say that the transition is not complete because we've had like a full finalization cycle on the beacon chain. And then we basically stop gossiping anything related to proof of work altogether on the network, and the transition is marked as complete. So if you're, say, an application or an exchange or somebody that needs to handle reorgs, this is kind of the point at which you can be certain that a reorg is not going to happen and the transition has taken place. And this entire process probably only takes something like 15 minutes. So it's going to be quite quick. Ideally, in kind of the best case scenario, that there are no or very few reorgs, like not more than you'd see, but there's kind of no condition under which the change just stop. It should keep progressing, and in the worst case, you're just going to have kind of a fair amount of reorgs right around that TTD block. And so if you're kind of using an application or something, you probably want to just increase the amount of confirmations you're waiting for, ideally all the way up to the finalized block. So I know this is a lot. I have a graph here that explains this. Also, shout out to Danny Ryan. He's the one who put together all these graphics, not myself. He's done a great job here. But yeah, so this kind of walks you through what the merge looks like. If you start on the left side, you have these two parallel chains. On the top, you have the proof of work chain with the execution layer blocks in them, like we saw earlier. On the bottom, we have the beacon chain, which has all this consensus layer metadata, but doesn't have any kind of executed. Then you have one block, you have two blocks on both sides. You can see here, it's almost like the second proof of work block would be the one which exceeds terminal total difficulty. Then the block after that would actually be produced by the beacon chain. So within the beacon chain, we now have execution layer blocks, execution layer payloads, which contains all of the transactions. And then we just keep going for that. So, the next block is fully produced on the beacon chain and also contains these transactions. And after that, the merge is done. So final thing I'll say is, there's a lot of work to do to get this, to make this happen. We have a public checklist that we keep here. I'll have a link to the slides, so if people want to click through. The screenshot is not up to date, but if you're interested to understand, how far along are we, what's left to do, or potentially help with some of these initiatives, this merge readiness checklist is the place to go. Slides are available here, bit.ly/ETH-21Q4. So if you want to get a copy, to click through any of the links that I had in there, feel free to. And that's all I had. Happy to take some questions. I see there's already a couple in the Q&A.
Yeah. We have a couple questions. First, thank you so much for presenting. That was awesome. I know I'm super excited for the merge, so it's great to get some more insight into that. So the top question we have is, are you able to speak a little bit about the recently proposed EIP 4488, perhaps in ELI 5?
Yes. So I'll start by saying I'm literally working on a blog post for this that should go out tomorrow. So I'll share it on Twitter. So at Tim Beiko, I think I have this here. So yeah, my Twitter is here. If the full explanation, please read that. Explain like I'm 5 though. So EIP 4488 proposes to reduce the cost of call data associated with transactions. Call data is basically, you can think of as data that you put in your transaction. If any of you have ever gone to Etherscan and seen kind of a message that's included in the transaction, that's call data. The reason why this matters is when you do transactions on rollups on Ethereum, what they do is they run all of your transactions on the rollups, but then all the data from your actual transactions get posted back on mainnet. So on mainnet, you're not actually executing that transaction, but you have all the data to execute it if you wanted to. Therefore, the cost of rollup is directly proportional to how much it costs to store data on mainnet, which is the call data cost. EIP 4488 proposes to reduce this cost by 5x. And the reason why is that rollup transactions today are still, relatively cheap, not like they're cheap. It's about a couple dollars to send tokens on Optimism, for example, or Arbitrum. And you can imagine, say that, the usage for rollup, like the demand for rollup goes up 10x, 100x in the next year. These costs will also go up because they need to post back the transaction data from everybody to the main chain. So if we can reduce the amount that it costs to do that in a safe way, then we probably should, because we're kind of keeping, it is kind of a cost reduction for rollups right now. But I think that the way I think about it is really, it's kind of proactively addressing the high cost that we're going to see in the future. So it makes it, maybe in a year from now, we're back to the current set of fees and not 10x higher. So kind of the gist of it. Again, I'm going to try and write a post, or start writing a post. I'll try and publish it tomorrow, which goes into the details as soon as I have it.
Awesome. Well, I'm stoked to read that. Great answer. And so question that's been getting a lot of traction, it seems, is, do you foresee NFTs being pushed over to their own side chains in order to reduce gas surges / wars on mainnet?
I think so. I think over time, most of the usage is going to be on rollups. There'll be very limited use cases for end users to use the main chain, just because, the main chain is always going to have a limited throughput, and if the demand keeps growing, then the fees keep growing as well. Whereas they're much easier to manage on layer 2s. So yes, I do think that in the future, basically most, if not all, NFT drops would happen on their own chains. And I also think we're going to interesting mechanisms for the actual drops. We're already starting to see that a bit, but the NFT drops from today basically resemble the kind of ICO drops from 2017, where it's first come, first serve, and that creates huge gas wars. I think we're gonna start seeing more and more cases where like people just design these jobs more intelligently, and they kind of reduce the amount of gas margins that you need to participate in the sale.
I mean, that absolutely makes a lot of sense to me, and I would agree with your answer. So then we have another question. When ETH2 comes online, do you think sidechains will by and large become irrelevant, or will they still have a relevant place in the ecosystem?
Right. So I think all of the rollup chains will be extremely relevant because they're the main way by which we scale computation, right? So all the transaction, most of it will move there. There are side chains as well. So stuff like Matic, I think they will stay relevant. The trade-off there is basically on a proper rollup like Arbitrum or Optimism or Starkware, you can always withdraw your funds by going back to L1, even if the rollup operator is malicious or offline or whatever. On a lot of these side chains, you actually can't do that. So this, I don't want to like assume ill intent or anything here, but like, if you deposit ETH on a side chain and for whatever reason that side chain goes down, or the contract that they have on mainnet that stores the ETH gets hacked or gets compromised, you can actually lose all of your funds. And depending on the design of the side chains, there are some cases where can actually decide to steal all of your funds because they have access to them on L1 and they can just send your ETH to themselves. That basically trade-offs usually though comes with the benefit that the transactions are much cheaper on those side chains than they're on proper rollups. So I think we might see use cases which make a lot of sense for side chains where like, the value at stake for most users is quite small and, they're comfortable with the security assumptions. And in practice, we do see it. But I think if you think of like most of like the, censorship resistant usage that you see on Ethereum, I suspect all of that moves rollups or the very large majority within the next couple of years.
Yeah,
the next question is about Polkadot. I'm not familiar enough with Polkadot. Like I think high level, they kind of operate similarly, but there's a ton of technical details that unfortunately I'm just like not familiar enough with Polkadot's architecture to comment on. But generally, yes, they serve the same role with just different security and trust assumptions.
Yeah, so then if you have time we have two more questions.
Yeah, sure. Yeah.
So,
okay, so how do we deal with fragmentation of liquidity amongst L2 Evm chains? I mean, there is bridges. You have bridges to move things across. And you can imagine having some sort of aggregators, kind of like the equivalent of like 1inch or Matcha that just works across all the chains. So say you want to like sell $1 million of ETH or whatever, it just routes your order to all the chains and whatnot, and you pay fees for that. So I think there's basically going to be probably a trade-off between like how instant do you want your liquidity to be, and like how cheap of a fee do you pay. I think there's a lot of cases where like you can probably get like very quick liquidity, very expensive, and route kind of behind the scenes through all the chains, or you have just like lower liquidity and cheaper execution, but it might take you a bit longer. Yeah, so I think there's a bunch of market equilibriums there, and different like user personas will optimize for different things. Last question, but not least, is there a rough timeline for this merge to take place? Timelines are always hard. The reason is, we can assume everything goes well, but then something breaks, and we obviously want to fix that. So everybody's priority is getting like a safe merge rather than a quick merge. That said, I suspect the first half of next year makes sense. What we're aiming in the month of December to have a kind of long-lived testnet that's up and running for the merge, which we can get applications and infrastructure and tooling to start using. The big open question about how soon we can merge on mainnet is just, how much applications are ready for the transition. Luckily, at like the smart contract side, there's not going to be any changes required. But for stuff like say Infura, Etherscan, MetaMask, and all those folks, you want to make sure that they support the merge. And it's a bit more complicated than previous upgrades, so it's not clear, exactly how much time they're going to need. We've started having community calls with folks. We have one coming this Friday so that we can proactively take their questions. but yeah, I think that's the other kind of wild card. So basically, you know, do we hit any unexpected bugs, and then is the community tooling, infrastructure, and whatnot kind of ready to support the merge? Those are really the two big things. But I think generally, if things go well, yeah, first half of next year should work out.
One more question that just popped up.
Right.
Well,
Okay. Yeah. So
yeah, you got it.
yeah. So basically the goal at this point is to just have data on shards and not actually store computation, where you move the computation just to rollups. And then you use shards as a way for rollups to store data even cheaper. So like I mentioned, we had this first question about EIP 4488. So EIP 4488 lowers the cost of storing data on mainnet. But if we have shards whose sole purpose is to store data, then we can lower the cost even further on those. I'm not sure exactly how many shards we're going to have, but none of them will store kind of a computation state. The rollups basically store those, and obviously they all have a unique state per rollup.
Awesome. Well, thank you so much for being here, Tim. I myself, and I'm sure everyone else in this call, is super excited for the merge and is super grateful for the work that you do in facilitating it and helping push development in the ecosystem. So it's an honor to have you. Thank you so much for coming.
Thank you. This was great.
Cool. Hopefully see you soon. Feel free to stick around. We'd love to have you.
Cool.